in Matter Labs, and he is our 4844 expert. So for that section, we borrowed liberally from Zach's slides, and yeah, so we're in deep debt to him, and we'll draw on him if needed. Just to introduce Matter Labs. So for certain projects, Arbitrum is another one. There is a separation between the company that actually launches the network and then the network itself. And this is true of Matter Labs. So Matter Labs is a company of about 115 people, based primarily in Europe and Asia. And we launched zkSync, the zkSync Lite and zkSync Era. zkSync Era is a general purpose zk EVM, which we'll get to in just a second. But just briefly about the company, we have jobs open, so check out our jobs page. But if you wouldn't mind going to the next slide, Sid. I'm sure a lot of you are familiar with L2s. Some of you may have also heard of zkSync. But we are what's called an EVM compatible zk rollup, and we'll get into that a lot in the next 2 weeks over these sessions. But essentially, what a rollup does is it compresses transactions into a single transaction that gets committed to an L1. And it does so trustlessly, meaning that if there is an issue or a dispute or some sort of network corruption on the L2, L2 design is required to have a mechanism by which people can exit using the L1 smart contract. And so it's considered to be it inherits the security of Ethereum. L2s typically do. We'll get into that a lot more as to why we need that and all that sort of thing in this lecture today. But just to sort of from the top, Matter Labs is the company that Zach and myself worked for, and Hope, who was there earlier. And we launched this network zkSync last May, right after East Denver last year, and it's been running for about a year now. Next slide, if you don't mind. So just a brief word about the workshop series, and then I'll toss it over to Sid. So layer 2 networks are a very popular discussion and very popular projects right now, as are zk EVMs, which are a subsection of L2s. However, it's sort of unclear kind of what those are to a lot of people, and so as part of our mission, not only as sort of developing a network and establishing this project and bringing scalability to Ethereum, Matter Labs also sees as a responsibility, almost like a public good, to be able to educate the ecosystem, including you all and people at different conferences and universities around the world, about just sort of having a common understanding of what an L2 is from an agnostic standpoint, not just from zkSync standpoint, as well as being able to deeply understand what zero knowledge proofs are and how they're applied to create zk EVMs. And the reason why we want to do this is because the fundamental premise of blockchain is don't trust but verify. And that's very hard to do today with L2s because just the fundamental technical understanding is missing. So we are on a mission to be able to educate folks about the concepts and foundational stuff that's underpinning L2 systems and zk EVMs, with the hope that it'll allow folks like you to be able to contribute more, to contribute to discussions, contribute to the tech itself, and just have a better understanding of this, what I think could be an extremely pivotal technology for crypto, as we'll see in a little bit. So we're doing this workshop series. Today is L1 fundamentals through the lens of L2. So I know a lot of you all are familiar with L1 fundamentals, but we are going to focus on a few very recent innovations and see how they could be interpreted from the L2 perspective. And then the session on Thursday is going to be an overview of L2 systems from a universal standpoint. We have this universal mental model that can be applied to any L2 network, and we're going to go through that discussion as well. Third series is going to be around designing circuits from a very high level, just understanding what a zk EVM system is and what circuits are and what provers are, that sort of thing. And then the last is going to be sort of advanced and sort of interesting grab bag of what else is happening in the zk space, such as zk machine learning, decentralized identity, that sort of thing. So with that, we really hope this is an educational and meaningful experience for y'all. And we're really, really excited. We also have designed custom swag just for you all. We're really excited. I had hoped to grab me a couple sweatshirts for Zach and myself. So I hope people are able to get that and enjoy that. And yeah, I will hand it over to Sid. Thank you all so much, and thanks for being here.
All right, thank you, Coogan. So yeah, now I'll do a brief intro on myself. So as you guys know, I'm Sid. I'm currently doing a master's here, where I focus on research on consensus protocols at the Sky Computing Lab here at Berkeley. So part of my research focuses on DAG-based BFT protocols. So if you guys have ever heard of Narwhal and Bullshark, they're more novel protocols that focus on high throughput for consensus and working on getting lower latency there. And I also do some work on Gasper, which is Ethereum's consensus protocol. And here at BAB, I used to be ex-Copres, developer and researcher, and now I'm just giving lectures for fun. So yeah, that's a little bit about me. Now let's talk a little bit more about BAB for those who are unfamiliar. So we're a student org here at Berkeley focused on education, research, development, and design in the blockchain space. So we run courses on campus and online, if you guys have ever seen our edX. We do consulting projects with Fortune 500 companies and top blockchain companies, and we have past research projects as well. And if any of this is of interest to you, feel free to scan this QR code to learn more about us. And yeah, are there any questions before we dive into like our overview section? All right, awesome. So let's do a brief overview on crypto. So Bitcoin and Ethereum are two of like the most well-known things in the industry. So let's talk a little bit about Bitcoin first. So Bitcoin is the first widespread cryptocurrency application that solves the Byzantine generals problem. So the core innovation that Bitcoin did is proof of work consensus. So the Byzantine generals problem basically explains how do computer networks continue functioning when you can have up to F parts of the network fail. And the proof of work consensus protocol solves this by making the network solve computational puzzles to prove that they are not malicious or non-faulty. And if they provide a correct solution to the computational puzzle, then whatever transactions or blocks that they're trying to add to the network can get added. And this is kind of what we show in this diagram here. So let's move this a little bit. Let's minimize really quick. So we say client and server in this diagram, but you can think of the client being just like any node on the network, and then the server being the broader network. So one of the nodes in the client solves the computational puzzle. They send it to the network to verify this. And once it's verified, they are granted the service, which is essentially just like adding a new block to the network. Now let's talk a little bit about Ethereum. So Ethereum very broadly kind of just generalizes the Bitcoin concept by adding a programming or execution environment. And this is very powerful because you can do a lot of more generalized applications or just pretty much almost anything on this very distributed computer that a lot of people have access to through this like programming environment. So specifically the Ethereum blockchain uses what's called the Ethereum virtual machine, EVM. And this kind of acts as like almost every other computer that you know. So you have like a stack, memory, and program counter that kind of just tells you how to execute programs. You have access to some memory or state, such as like your counts here, and then other EVM codes that we won't really go into. And the core difference that Ethereum has than most other computers is this notion of gas. So gas is kind of just a way for you to measure how much computation your program is actually doing. So the main idea is that if you have some computation, you want everybody to pay for everything that they're doing. So you kind of use gas to denote how much work are you making the network do. Yep, questions? Between all the EVMs. So the Ethereum virtual machine doesn't really parallelize at all. It's like very poorly designed in that sense. Essentially, like everybody has like this notion of like storage slots which is like in your like computer when you have like RAM memory, it kind of corresponds to that. It's that everybody knows that in the virtual machine, this value is stored at this slot when you're executing some smart contract. So there's no real notion of like parallelizing. Other blockchains do this, namely like Solana has a lot of this type of optimizations, but Ethereum doesn't really have that provided. People are trying to work on this type of stuff, but it hasn't really been formalized yet. So kind of like a simplified but also complicated computer. So this is all like very kind of like nuanced stuff and very new. So now the obvious question to ask is, why is adoption not widespread? Do we have any takers? Any guesses? Sure. Okay. Anything else? Go for it.
There's a lot of bad actors like in the industry, and that can cause a lot of fear.
Mm-hmm.
There's a high like barrier for entry, like based on like the knowledge you have.
Mm-hmm. Yeah, so these are all pretty good responses, and yeah, I pretty much agree with all of them. There's a lot of growing pains around accessibility or UI. It's very expensive to use the system sometimes, and it's very new technology, so a lot of people don't really know how a lot of it works, which can lead to bad actors taking advantage of this, and it can just be difficult to kind of use the systems. So this kind of leads into what's called like the blockchain trilemma, where people try to balance between decentralization, scalability, and security. And typically you get to choose two of these three. So Ethereum specifically has this kind of ethos where they focus on, for blockchain to be decentralized, it's very important for a normal person to be able to run a node and be able to verify things on their own. It's this notion of trust, don't trust, but verify. And this has been very commonly quoted by Vitalik, the co-founder of Ethereum. So Ethereum has a goal of keeping the hardware requirements low for you to run a node. And any updates to scalability should not come at the expense of decentralization or security. And the way that Ethereum approaches this today is the idea of L2 networks on top of Ethereum, also known as rollups. So L2 solve this blockchain trilemma by compressing many transactions into one transaction that's submitted into the L1, and they do so in a trustless way. So you can imagine that if I'm using an L2, I treat it the same as transacting on Ethereum, but under the hood, the L2 just compresses a bunch of information on this like separate layer that's cheaper, and then submits it back to Ethereum for everyone to use. And it does so in a trustless way so that you can dispute things and also like trustlessly exit the L2. So yeah, rollups perform transaction execution outside of the layer one and then post this data back. And Ethereum has kind of like changed their scalability roadmap to focus on this rollup centric model because it allows people to focus on decentralization and security of just the Ethereum layer while not having to worry about scalability of other things that you're using. So it kind of reduces the scope for Ethereum to work on, but also allows people a lot of design space to do other things. And rollups are a lot cheaper than L1s, mostly due to the L1 fees. And we'll dive a little bit more into that, but we'll just leave it at that for now. But I do want to say, like, L2s are not a very novel idea. So Ethereum's been around for a while, and L2s have been suggested back in 2015 as a way to do scalability. So a nice analogy to think about L2s is kind of like interstates and highways. So you can consider the L1 to be the interstate that's designed as like the backbone of transportation and designed for like long distance travel and just like a lot of things, and is very stable to think about it. Whereas an L2 is like a highway that's parallel to the interstate. So it can also facilitate traffic, but it's probably used for like shorter distances and whatnot. And you can interlink the two between an on-ramp and an off-ramp. In this case, it's through a smart contract bridge. And this allows both systems to interact and exchange assets securely and efficiently. So when you have high traffic on your interstate, what do you want to do? You would want to take the highway as it's like easier to get on and off and just faster. So the same analogy applies to L1s and L2s. When there's a lot of traffic on the L1s, a user may decide to use an L2 for a period of time for cheaper and faster transactions. And then they can eventually choose to say, okay, I'm done with the L2. The L1 is back to normal. I want to continue using the L1. So yeah, that's kind of just like a nice analogy to reason about everything. So rollup provides like a critical component to give security to the L2 user through two main mechanisms. The first is that L2 users should be able to take whatever they have on the L2 and bring it back to the L1 without any coordination from the L2. So this is why we have smart contract bridges. And without this guarantee, you wouldn't have like a trustless implementation of the system. And then there's other mechanisms to make sure that your transactions were executed correctly in the first place on the L2 that we will also dive into. And yeah, since they have been proposed in 2015, rollups have kind of become like the canonical way to make Ethereum more scalable by just compressing transactions in a trustless way. And they're seen so critical that Vitalik, once again, the co-founder of Ethereum, thought it's like the best way forward. Previously, Ethereum had like a slightly different architecture to scale, but since then that's been kind of discarded and is focusing specifically on rollups. And the Ethereum core developers are making changes just to make Ethereum better suited to run L2s. And this is one of the posts on the ETH research forum, I believe, that kind of discusses this. And yeah, we're going to start off by focusing on two main things: the merge and the separation of consensus and execution on the L1 and how this relates to L2 networks. But before we dive into that, are there any questions? All right, cool. So now let's talk a little bit about the merge. So the merge was Ethereum's transition from proof of work to proof of stake. So we talked about proof of work a little bit earlier, where we like described it as like a way to kind of just like have computational puzzles to be able to prove that somebody's not like a bad actor. What we didn't talk about is that it's very inefficient amongst other bad properties that make it kind of like an undesirable way to run blockchains. So the merge was basically Ethereum's upgrade to the proof of stake model of consensus that we won't really worry about for now, but let's just, we just think about it as a different way to run the network. So the existing proof of work blockchain was replaced with what's called the proof of stake beacon blockchain. So the pre-merge beacon chain had not been processing transactions. Like we can see that we started the beacon chain somewhere here, but it wasn't really doing much work. It was just reaching consensus on blocks. And then after the merge, which is like an arbitrary point the Ethereum developers set, they said, okay, we're going to move to this new system. So with the merge came this nice separation of concerns. So previously, the Ethereum 1.0 blockchain kind of just had like one like execution layer that just did all of the work. But with the beacon chain, we separate the execution layer from the consensus layer. So as we see here, like the execution layer in like proof of work Ethereum just contained like a bunch of transactions and other like metadata that's important. But then after the merge, we have the separation where the consensus layer tells us like, oh, this is how we like process new transactions and order them. And then it kind of sends it off to a different layer to actually execute the transactions. We can kind of see this more explicitly here, where an Ethereum client is made up just of like two different parts: the beacon node, which is the consensus layer, and the execution engine, which communicates with the beacon node to be able to execute transactions. So the beacon chain handles proof of stake consensus, and it tracks like the chain's head, any like new blocks that are being gossiped, and receives like validator rewards. And the execution layer just primarily handles like running transactions and running smart contracts and updating the state of the Ethereum blockchain. So everybody that runs a node essentially runs both of these two pieces together, with some exceptions. And this is what's happening like under the hood when you're interacting with the Ethereum blockchain. So the data layer in Ethereum is technically just like the beacon chain state, which is essentially, you can think about like all the accounts that exist in Ethereum and like what balances they have. Different blockchains have different approaches to this, but on Ethereum, it's kind of just like everybody just has like one like beacon state that every validator just maintains. All right, and now we're going to talk a little bit about client diversity. Like we just mentioned, like Ethereum cares a lot about decentralization and security. So there's a lot of different clients to do this. So on the left side of the screen, we have all of the execution clients. So you can see that they're written in like a variety of different languages by a variety of different developers. And on the right side, we see all the consensus clients, also in a variety of different languages and frameworks and developers. So the goal here is to kind of just make sure that there's a very little overlap and like systemic risk in the system. So like, let's say there's a bug in one of these clients. If it goes down, then we want other clients to be able to take over without having a lot of failures. And this is kind of just made a lot more explicit with the separation between the consensus and the execution clients. So with that being said, what does this mean for L2s? So the L2 transaction lifecycle kind of looks like a single transaction in mainnet, but in reality, it kind of follows like a similar process to what we just mentioned for L1s. So this is like kind of like the full picture, but we're going to make this a little simpler and not worry about forced transactions. So let's just consider this simplified picture. So if I'm a user on an L2, I submit my transaction to the sequencer. And the sequencer takes a bunch of transactions, puts it into an L2 block that's unverified. We can consider this to be kind of similar to the consensus clients, like just ordering different things and figuring out, okay, I have a bunch of transactions, how do I package them together? Then the unverified block is posted onto the Ethereum layer and sent out to the prover. And the prover generates like a zk proof that tells us, okay, these are like valid transactions or they've been executed correctly, generates a proof, and the proof is sent to the L1 as well, which is kind of similar to like the execution part of the regular Ethereum L1. So we kind of see like the same idea of like separation of concerns between the sequencer ordering and then proofs being generated, which is essentially like making sure that everything works correctly or executing in a broad sense, and then putting that back down into the Ethereum layer. I know that was a lot. Are there any questions about how this works or just like anything in specific? Go for it.
Layer 2 security and layer 1 security completely separated. I mean, if someone does take 51% of control of the market share for layer 2, basically they improve whatever they want on Ethereum.
Kind of like there are mechanisms to be able to prove that some transaction was faulty. Like in optimistic rollups, there's a concept of fraud proofs that you can run to say, oh, like, look, this person did this incorrectly. And in zk proofs, it's slightly different because if your proof verifies in the first place, that means that it follows all the rules of the VM. So that kind of just like, if it doesn't prove, then like there's a bug in the first place, which, so kind of like, in theory, it shouldn't be possible to construct in the first place. But I wouldn't say that they inherit security, because if you're an L2 user, the only thing that you care about is like the L1's ability to do what you want it to do. Like if you send some transactions into the L2 and then that goes into the L1, you just want to make sure it makes it to the L1. And then you also want to be able to make sure that the L1 works correctly for you to be able to take anything you have on the L2 off the L2 without interacting with the L2. So I think the better way to think about it is that the L2 inherits the security of Ethereum, and it kind of requires that to be able to function like a trustless way.
From layer 2 to layer 1, other transactions compressed or just like the same amount of data just verified quickly.
Usually ends up being compressed. Like for example, for zk proofs, like all you need to show is that there's like a state diff. Like basically all you're saying is like, oh, this was the state of the L2 before this block, and this is what this block did that's different from that. And then you prove that that like transition was correct. So that's like that ends up being a lot smaller than like proving or like listing out every single transaction itself. So it does end up being compressed. Yep.
Sorry, for the sequencer, is that decided by whoever is like the user, or is that decided by the node that's doing the rollup?
It's decided by the rollup.
Oh.
Yeah. Right now, there are a lot of people doing research into decentralized sequencing. A lot of rollups today don't really have like a decentralized model for you to be able to like spit up your own L2 sequencer. But people are working on that. Yeah. But even if the L2 did act maliciously, you should be able to, there are like mechanisms to be able to prove that it acted maliciously. So that is kind of just like makes life easier.
I guess like the follow-up question is like, is there like some pseudo malicious ways that it could act where it's not technically wrong? Like, let's say like there was some trade that both the person hosting the L2 wanted to make and you wanted to make, did they choose to put theirs over yours sort of because they're cheating the sequencing?
Yeah, they could do that, but it's also kind of easy to tell. Like, if there's like if the sequencer was actually doing that, you would be able to tell, oh, this account is owned by like the sequencing company. Like, they're just like doing this. So it is easy to tell. I guess it's more of like a social thing. But yeah, it is kind of hard to like fake that. Yeah. All right, let's move on to our next section, which
Before we go on to the next section, we're gonna take a break, and everyone can grab some pizza and wear some cool merch that we have. We have some, wait, we have some ZK and Fab and exclusive edition merch. Like you cannot find this anywhere else. So please grab some pizza. Yes, what? No, you have to come.
Shoot it.
Oh.
Oh,
Oh, you're right, I should shoot it.
put me in coach. That is. Wait,
Wait. Okay, please grab some pizza.
Yo,
Right.
No, you're good. All right, everyone, we're going to go ahead and get started again. So we're going to talk about data availability and EIP 4844. One of our audience members, Numan, suggested or kind of alluded to this earlier. So we're going to talk about it a little more. Data availability is a fundamental concept for any L2 implementation, and it refers to the assurance that any necessary L2 data, such as transaction details or the current state of the L2, is accessible from the L1 and can be independently verified. So this is kind of like a visualization of what L2s are, or what L1s and data availability are with respect to L2s. So for understanding an L2, you kind of have to know where the data for it is stored. Another way of kind of putting this is what is the network's data availability layer? And once again, it's very crucial to maintain like the trustless nature of the system, because it ensures that anybody can verify the transaction and inspect it. The difficult part is that when you're scaling blockchains, the blocks end up getting bigger, and it becomes harder for normal users to download the data all the time and verify it as you kind of want to. And once again, Ethereum has like this core design goal of being able to do that for any arbitrary person with low hardware requirements. So once again, the importance of data availability in L2s can be overstated. And without that, it kind of goes against the ethos of decentralization and trustlessness. And it becomes impractical. And it just makes it a lot easier for people to potentially manipulate the L2 and do fraudulent things. So traditional L2s use Ethereum as the data availability layer. And this is why we say that L2s quote unquote inherit the security from the Ethereum state, from the Ethereum base layer. And yeah, so the Ethereum state combined with the L2 state root, which is essentially just like a hash of all of the accounts and their balances in the L2, can be used to dispute transactions or claim fees. And that's why we say that it's inheriting the security guarantee of Ethereum mainnet. So going back to this diagram, L2s use L1, the Ethereum L1 for data availability. But once again, we said that this was a hard thing. And so the Ethereum core developers have been modifying the Ethereum core protocol to introduce an update known as EIP 4844, also commonly known as blobs. So it increases the space from like roughly 50 to 100 kilobytes of data to roughly 1 megabyte per L1 block, and creates a cheaper separate fee market for this additional data that is specifically designed for rollups. So once again, kind of just underscore the main point. This is a change that's being proposed for Ethereum as a base protocol and not just like a specific L2. And once again, once it's implemented, it'll allow L2s like zkSync to lower costs, which is once again one of the greatest barriers of entry to adoption. And like the reason it lowers cost is because like we had in the previous question, L2s need to post some data onto the L1, but you want this to be cheap. You don't want to compete against the congestion of the Ethereum base layer itself. Like if the Ethereum base layer is congested with a lot of activity, it can be difficult for L2s to get their state data posting in on time. But having the separate transaction type and way of storing data makes it a lot cheaper for them. So blobs are cheap and temporary storage, and they only need to be stored for about 18 days, and they're stored on the consensus layer. So once again, going back to our separation of concerns, they're only stored on the part where people reach consensus on what transactions are being ordered and how they're processed into blocks. An important kind of consequence of this is that it is inaccessible to our execution environment. And instead of being able to see the blobs itself, we can only see cryptographic commitments to the contents. We won't really dive into a lot of the specifics of the cryptography, but we do kind of use this as a tool to understand what L2s do better. Each blob holds about 125 kilobytes of data, and we have a target of 3 blobs per block with a maximum of 6 blobs per block. And once again, to make it cheaper, we have like a multi-dimensional fee market, which offsets like standard congestion. So instead of competing against all transactions, you're just competing against L2 transactions in terms of pricing. Questions? We will answer this in the next slide. All right, so this is kind of like the blob lifecycle. So an L2 user submits a transaction on the L2. The L2 operator or sequencer bundles a bunch of them together or produces like a state diff and generates a blob transaction with embedded blob data. This blob then goes to our L1, so it goes to Ethereum, and it's added to the execution environment by the beacon chain through what's known as like a sidecar. It's essentially like extra software that runs with your node. Once it's in the beacon chain, for L2s, you can see this data for up to 1 month. And after that, it's kind of just like persisted in the L2 state. And then the blobs stay in the execution payload in the L1 forever. So you will have cryptographic commitments to the L1, to the blobs in the L1, but you won't be able to see the exact data itself. You just need to know how to access the commitments. And this is like available forever. So I think if we, yeah, so like every block in the consensus layer has some information about what you need to do in the execution layer. So it just stays in that like part of the block on the consensus layer. So it's just like a part of the block essentially. But it expires technically on the L2. Yep.
Can you access the encrypted data that is sent by the blob after the 30 days? Like after the month where it leaves the L2?
Yeah, so once it's in the L2, you'll always have the commitments on the execution payload. And using cryptographic magic, you can access the data without knowing the exact contents. So yeah. We'll dive a little bit into that. Are there any other questions? All right. So yeah, this is kind of like another visualization of the life cycle. It kind of just goes through like the same logic. Maybe this is a little bit easier to understand. This is what we're talking about in the execution payload. Like every beacon block that's proposed in the consensus layer contains an execution payload, and the blob would be kind of adjacent to that. And then the execution environment has like a new opcode to be able to like pull a given blob's like version hash. So you can like pull a blob from some part of your like some previous blocks and access the commitment data essentially in the execution layer. Now we can talk a little bit about how we can reason about what's inside blobs. But before that, I'm gonna bring in Zach in case he has anything to add on to what I said. Zach, do you have any thoughts?
No, nothing to add so far. I think you've pretty much hit the nail on the head.
Awesome. Yeah, feel free to interrupt as I go through the rest of the slides with any more details that you might find necessary.
Sure
But
thing.
yeah, we're gonna go ahead and talk a little bit about how can we like reason about blobs if we don't have access to the data itself. So there is a construct in magic cryptography land known as KZG commitments. It was made by 3 very smart people. I just know the K stands for Kate. He's like a professor, I think. And technically, if you're trying to just like think about blobs, like, and you want to have some data, but you don't want to be able to like see the exact data itself, you could just hash the data. But that doesn't really work out because it doesn't provide like a lot of information about what's underneath the data. So it's not really an ideal solution. So instead, there's a construct called KZG commitments. which is a form of polynomial commitments, which you guys don't need to really understand. But it's used to kind of represent the blob data. And using these commitments, which are, you can kind of think of it as like a compressed representation of the blobs, we can prove what the data represents with strong mathematical guarantees. So we have this idea of like proof of equivalence, where we need to be able to like reason about the data in the blobs. But once again, the blobs that carry transactions no longer have access to the contents, but we have access to the commitments. So the Ethereum virtual machine has this optimized way of doing cryptographic operations. And with the KZG commitments, we can open the commitment at a given point and see if it yields some value. And using that, we can reason about some of the data. I understand this is kind of abstract. This is for you, those of you that are a little more mathematically inclined to learn a bit more about KZG commitments. But basically, blobs plus cryptographic magic allows us to reason about what's inside it without actually looking at the data itself. Zach, any thoughts?
Yeah, so with you can kind of think about polynomial commitments versus just hashing the data as if I want to prove that what the data that formed a hash was, I have to reveal the entire contents, which is not only inefficient, but in the scope of zk reveals all of the information. Whereas with a polynomial commitment, I can basically go and prove that I know that a certain byte represented by the commitment is a certain value. And so we can use the KZG commitment, the point, I would say byte index might be a good way of thinking about it, as well as what that value is, and prove that the blob actually, the KZG commitment actually represents that blob.
Are there any questions about KZG commitments / blobs? All right. Now we can talk a little bit about the pricing aspect of it. So how do blobs help with Ethereum gas pricing? So essentially, we talked about this a little bit earlier, but Ethereum uses gas as a way to measure how much computation is being done in a smart contract. And we kind of extend this idea to blobs to have like a different way of measuring how much data is being stored through blobs. So it works very similar to the current gas mechanisms that Ethereum provides for smart contracts. And each blob transaction specifies like the same parameters. So EIP 1559, which we don't really need to worry about, but we can think of it broadly as like gas stability, allows users to specify max fee per gas. And with EIP 4844, we can specify how much gas we want to pay per blob as well. So this helps us decouple the demand for blob data versus call data and other operations that happen on the virtual machine layer. So when like the gas prices on Ethereum surge because of like whatever transactions are happening there, this is not priced or does not change the pricing that rollups need to pay to be able to access the L1. And this is very important. We can kind of see this in this table here as well. So without blobs, the average block size is 85 kilobytes with a worst case size of 1.8 megabytes. But with reduced call data EIPs, we can increase our call data by 5x to 350 kilobytes, have smaller worst case blocks, which is much better for our kind of like tail case of users that may not have the best hardware. And ideally with a full proto-dank sharding approach, which is like the blob-based approach and rollup-centric roadmap, we want our average blob size to be a bit larger at 375 kilobytes. but we also want the worst case blob size to be smaller to allow for a wider diversity of clients and people participating in the network. Are there any questions about this, like economics or like the market side of L2s?
Just to add in one thing. So to kind of see what the effect of using blob versus posting the same data via call data. It was talked about, gas was talked about earlier, and gas is fixed per L1 block. And given that the amount of data that we're posting is not accessible to the EVM, we actually get a drastic reduction in how much gas it takes up, which allows you to perform more computation. So some back of the napkin math showed that given given a full blob's worth of data, if we were to post it via call data or if we were to post it via blobs over call data, we actually get a 93% reduction in the amount of gas that's used. And keep in mind, this is separate from the costs associated with the fee market.
All right. Thank you, Zach. Yeah, any other questions? All right, awesome. Now we will talk a little bit about L2s as playgrounds for L1s. So kind of like, as we mentioned, Ethereum has a very high cost of failure. This is because Ethereum holds like a lot of like secured value. I think like all of the validators combined provide something in the order of like billions of dollars worth of security. So if you mess something up on the L1 side of things, it ends up being very, very costly, very, very quickly. And it's just like not a good place for experimentation. And we can also kind of see this in the way the Ethereum network has been adding changes and upgrades recently. It's been a lot more deliberate, a lot more slower. There's been a lot more complexity added to Ethereum as a base layer, which makes it, once again, not very ideal for experimentation and just trying new things. And that has changed with L2s. Because L2s make things a lot cheaper, they're a lot more nimble, you have a lot more control over what you do in your own kind of just like computation. And you need to follow like very simple rules in terms of like the guarantees you need to provide users in terms of posting data to the L1 and being able to withdraw things. L2s can be a lot better for experimentation. Like you can try different things. It's fine if you have some downtime. It's fine if you like suffer hacks and whatnot. None of this is truly desired at all in the first place. But if it happens, it's much better to do this experimentation and failure on an L2 than on the Ethereum base layer. And yeah, I think that's pretty much all that we had for this set of slides. Are there any questions before I talk about what we have coming up next? All right, sweet. So our next lecture in this series will be on Thursday, located in Moffett 106. I believe it's at the same time, 8 to 9:30 or 10 p.m. And we are going to be talking about an L2 deep dive and our like universal mental model for L2s. And it'll also be taught by one of our very special Blockchain Berkeley lecturers. And yeah, you guys should all be there for it. It should be very exciting. It should cover some of the stuff that we talked about in a little bit more detail, specifically for L2s, and not kind of just like setting this foundation between how L1 blockchains work and then how this relates to L2s. So yeah, be there for that. Once again, here's a link to our slides. Thank you everyone for being here, and thank you for the zkSync team for helping us with the intro and any of the additional comments that they provided. So yeah, thanks everyone.